Analyze the continuous beam shown in figure by slope deflection method. The support B sinks by 10 millimeter. Take the flexural rigidity EI 4000 kilonewton meter square. Draw SFD and BMD. Here so far we have studied how to analyze the continuous beams with one end fixed, one end hinged, and one end is hinged, one end is overhanged. We have discussed so far the beams without any sinking of the support. In the previous videos we have observed that there was no sinking or settlement of any support. Here now we will discuss about the analysis of beams with sinking or settlement of support. Here in this problem, the support B sinks by 10 millimeter and he has given the flexural rigidity EI. First we have to find out the settlement of the support. Here the support B, that is sinks by 10 mm. Then first we have to write, the first step is calculation of the sinking in each span. That is, here this one is the given B. Here this end is fixed. This one is B. With respect to its original position, B is sinked by 10 millimeter. This is the new position of the support B. With respect to its original position, B sinks by 10 millimeter. This one is A. Here this one is support at A. This one is the rotation of the span. Here this one is D. This one is A. This one is B. This one is C. Here at D it is subjected to a point load. The span DA is 1 meter. It is extended beyond the support, that is overhanging, and moment of inertia is I. The span is 1 meter. In span AB, that is subjected to a point load of 30 kilonewton at the center. The moment of inertia is I. The span of this beam is a span of this intermediate span, that is 2 meter to 4 meter. Then the end span, that is BC, the length is 6 meter with moment of inertia 2I and subjected to a unit load, that is UDL of intensity 20 kilonewton per meter. Here with respect to this one original position, this span is rotated in clockwise direction. This one is clockwise direction. The slope is here, this one is theta. That one is rotated in clockwise direction. Similarly, this one is rotated in anti-clockwise direction. Here first we have to calculate the settlement in each support. Here this one is, if you draw the horizontal line, here the rotation is rotation of AB, that is clockwise, rotation of BC, that is anti-clockwise. Here this rotation is anti-clockwise. Here the sign convention, first you have to remember the sign convention. Here with respect to A, B, the settlement is in downward direction, delta is positive. Or if the rotation, that is one of the sign convention we have studied, the clockwise rotation. Here the rotation is clockwise, that is clockwise rotation. If the rotation is clockwise, then here clockwise rotation. For the span AB, there is a rotation in clockwise rotation. hence delta is positive. The settlement is positive. You can consider the sign convention like this also. Then anti-clockwise that one is delta is negative in different spans. Here this we have to remember, or in the beginning of this topic we have discussed about the sign convention. Here in this span, for this span AB, delta equals 10 millimeter. Here this one is with respect to its original position, this is settled by 10 millimeter in downward direction. Then delta for this span, delta 1 or delta AB, for the span AB, that one is plus 10 mm. Or convert this into meters, that is 10 divided by 1000, 0.01 meter. Similarly, for this one, that is, you can say this one is delta 1, this one is delta 2 for the second span. This one is minus 10 mm. Since the rotation is anti-clockwise, here it is clockwise, then this one is minus 0.01 meter. You can adopt any one, either the clockwise rotation and anti-clockwise rotation, or with respect to A, B is settled in downward direction, the deflection delta is positive. Similarly, with respect to B, A is at higher level. With respect to the right support, with respect to left support, this one is at higher level, then the delta is negative. Or the rotation, here the rotation is clockwise, that is delta is positive. Here the rotation is anti-clockwise, that is negative. Then the first step is, this is the first step to calculate the settlements for each span. Then FEM, that is fixed the end moments for each span. Here there are 3 spans, but the span ED is extended beyond the support and it is overhanged. No need to write the fixed end moment for overhang. Convert overhang into resisting moment. That is, here this one is overhang, this one is A, this one is D. At D it is subjected to a point load of 20 kilonewton and distance is 1 meter. Here actual moment is 20 into 1, that one is in anti-clockwise direction. Here the resisting moment, that one is 20 into 1, 20 kilonewton meter. MAD, that one equals 20 kilonewton meter. Here you can write no fixed end moment, no FEM for AD. We have to remember, no fixed end moment for the overhanged portion. Don't write any slope deflection equation for the overhanged portion. Then MFAB, come to the second span. Here first span is over, that is, now we can write the fixed end moment for MFAB. That one is MFAB. It is subjected to a point load at the center, hence the equation, that is WL by 8. Here this one is anti-clockwise, then W is 30, that is negative, into L4 divided by 8, that one is minus 15 kilonewton meter. Similarly, At the other end, that is MFBA. From the other end, here it is positive, that is 30 into 4 by 8, that one is clockwise, that is plus 15 kilonewton meter. Then MFBC, that is second span or third span. This one is first span, this one is second span, this one is third span. MFBC for the left support, that is anti-clockwise, and the formula is WL square by 12. W is 20 and L is 6 square divided by 12. That one is minus 60 kilonewton meter. Similarly, for the other end, that is MFCB, that one is positive, that is clockwise, that is 20 into 6 square by 12. That one is 60 kilonewton meter. Here one is clockwise, one is anti-clockwise. Then the second step, write the slope deflection equation. Slope deflection equation. Already I told that for the overhanged portion, you come from the left side, that is no slope deflection equation for no SD equation for overhang. Then here, by observing this, there is a slope at A, slope at B, theta C equals 0, since that is fixed and C is fixed. There is no rotation or no movement, neither it is permitted to move nor permitted to rotate in any direction. Then write the slope deflection equation for AB. That one is, here we have to write, that is the fixed end moment. Fixed end moment for AB is minus 15 plus 2EI by L. Here the length of AB is 4 meter. I is 1I in the bracket 2 theta A. The near end is A, far end is B, theta B minus 3 delta. Delta is point, that is positive, that is just now we have calculated 0.01 divided by L, 3 delta by L. Here if you simplify this, he has given the value of EI, then this equation becomes, that is 2 into 2, 4 EI, that is 4 into EI. EI value he has given as, that is 4000, that is 4000 into 4 divided by 4, that one is minus 15 plus 4000 theta A plus 2000 theta B minus 3 by 4 into 0.01, that is minus 30 minus 15. That one is, if you simplify this, that one is 3/4 of 2000, that is, then by simplification you will get this equation as 4000 theta A plus 2000 theta B. Here by substituting the value of the flexural rigidity EI, then this one is equation number 1. Similarly, write the equation from the other end, that is plus 15 plus 2EI divided by L inside of the bracket. Here we are writing the slope deflection equation from the other end, or far end, that is B. Here the near end for B is 2 theta B plus theta A minus 3 into delta 0.01 divided by L. Then this equation becomes, that is 2000 theta A plus 4000 theta B This one is here minus 15 for plus 15 gets cancels. This one is equation number 2. Now you have written the equation for slope deflection equation for BA. Now we can write for the second span, that is BC, M, BC, M, BC. Here the fixed end moment that we have already calculated, that is minus 60 plus 2E. The moment of inertia for BC is 2I and length is 6 meter. Inside the bracket 2 theta B, here the near end is B, plus theta C minus, here delta is negative, minus 3 into delta, that is minus 0.01 divided by L. Then if you simplify this, MBC equals, here this one is 2 into 2, 4 into 2, 8 divided by 6, that is 8 divided by 6, 4 point, that one is, here by substituting the value of 4 by, this is 2 into 2 into 2, that is 8 by 6, that is 4 by 3 into 4000. Yeah, that one is, here we will get after simplification, this one is 5333.33 theta B plus 2667 theta C minus 46.66 minus 46.66. Here theta C is 0 since it is fixed end. This one is 0. This one is equation number 3. Similarly, MCB, that is last slope deflection equation, that one is, that is plus 60 plus 2E into 2I divided by 6. Inside the bracket, here the near end is theta C plus far end is theta B minus 3 into minus 0.01 divided by 6. This one becomes, that is, here after simplification and by substituting the values, that is 2666.67 theta B, theta C is 0, that is plus 5333.33 theta C, that one is 0, plus 73.33. This one is equation number 4. Now we have got the 4 equations, that is 2 for each span, that is for AB, for span BC. Then equilibrium conditions, by applying the equilibrium conditions or equilibrium of the supports, equilibrium conditions. Here at A there is one joint, that is at A, MAB plus MAD, MAB plus MAD equals 0. Here there are two spans, the summation of the moments at A equals 0. Then you will get by adding these two, that is 4000 theta A plus 2000 theta B that equals 10. That is equation number 1. Here you will get an equation. Similarly at B, here at B, MBA plus MBC, two members are connected at B, then summation of those two equals 0. Here you will get, by adding those two equations, 2000 theta A plus 2000 theta A plus 9333.33 theta B, that equals 46.67. This is equation number 2. By solving these two equations, you will get theta A equals, solving equations 1 and 2. 1 and 2, you will get theta A equals, here you will get the unknowns. There are two unknowns and there are two equations. By solving these two equations, you will get the unknowns theta A and theta B. Theta A equals 9.99 into 10 to the power of minus 7. Here he has given the value of the flexural rigidity, hence here it is free from any flexural rigidity. It is numerical value. Then here the next step is final moments. The final moments are, by substituting the values of theta A and theta A, theta B, theta C in the above equation, you will get the final moments as MAD, that we have already calculated. We have converted the overhang into the resisting moment. That one is 20 kilonewton meter. That is clockwise. Actual moment is anti-clockwise, but the resisting moment is anti-clockwise. That is clockwise. MAB and MAD should be equal. This one is 20 kilonewton meter, but this one is in anti-clockwise direction. Then MBA, that one is again, that is 20 kilonewton meter. That one is clockwise. Then MBC, that one is minus 20 kilonewton meter, that is anti-clockwise. Here negative means that is anti-clockwise. MCB, that one is 86.66 kilonewton meter. That one is clockwise. Now we can draw the bending moment diagram for this one. That is, here this one is the given beam. To draw the bending moment diagram for this one, here this one is the given beam. This one is subjected to point load of 20 kilonewton over a length of 1 meter. This one is subjected to a point load of 30 kilonewton. This is 2 meter. This one is subjected to UDL of 20 kilonewton per meter over a length of 6 meter. This one is 20 kilonewton per running meter. This one is D, this one is A, this one is B, this one is C. Here, by extending these lines, here now we can draw the bending moment diagram for this one. Here, this one is the datum line. Here we can mark these ordinates. Here By observing these moments, here MED is, that is clockwise, that one is positive or clockwise moment, and MAB is anti-clockwise. This one is 20 kilonewton per meter, 20 kilonewton meter. Similarly, MBA and MBC are of same magnitude. One is clockwise, one is anti-clockwise. And then MCB, that one is clockwise, that one is 86.66 kilonewton meter. Here, to draw the bending moment diagram, first we have to draw the support moments diagram. Support moments diagram. Here, these are the ordinates. We will consider this one as the reference line. To the reference line, here we have to draw the bending moment diagram like this. Here, the ordinates, by observing these bending moments, all are hugging moments. Here, we will represent the support moments, hugging moments like this. Here, these are the ordinates of the hugging moments at different supports like this. Here, this one is 20 kilonewton meter. This one is also 20 kilonewton meter. Here, these are the ordinates of the bending moment diagram. This one is 86.66 kilonewton meter. Here, we will represent these above the reference line or bottom line. Here, the bending moment in this portion ED is, it starts from 0 to maximum value. The variation is a straight line. Here, these are all the negative bending moments. Here, now, in this band, the bending moment is, it varies from 0 to maximum value, that is negative bending moment. That is negative bending moment. Here, no other loads except this 20 kilonewton. Here, at this point, that is, there is a point load of 30, that is maximum bending moment below the point load. That one is 30 into WL by 4, that one is 30 kilonewton meter. Then here the bending moment is a straight line, that is triangle like this. Here you can draw the bending moment at support. The bending moment is 0, and below the point load the bending moment is maximum. This one is 30 into 4 by 4, that one is 30 kilonewton meter. Since it is subjected to point load at the center, here the bending moment diagram, this one is positive bending moment. Here the remaining portion, this white portion, that is cancels, that get cancels. Here in this portion, that is subjected to UDL, that is WL square by 8 is the maximum bending moment at the center. Here the bending moment is maximum, that one is curved like this. That one is, we can represent the bending, simply supported beam bending moment by a curved line like this. Here this one is negative bending moment in this portion. Here this one is positive bending moment. Here the maximum ordinate of bending moment in simply supported beam subjected to UDL, that one is WL square by 8, that one is 20 into 6 square by 8, that one is 90 kilonewton meter. Here this one is the bending moment diagram. Here these ordinates are negative ordinates at the support, and there is positive bending moment below the point load, that is 30 kilonewton meter. Here at the center the bending moment is maximum, that is 90 kilonewton meter. Then to draw the shear force diagram, here we can apply the equilibrium equations one by one. That one is summation of V equals 0. That you will get to draw the shear force diagram. Phi A, Phi B, Phi C are the support reactions we have to assume in upward direction. Here this one is Phi C. Then Phi A plus Phi B plus Phi C, the summation of all these three must be equal to total downward force, that is minus 20 minus 30 minus 20 into 6. Then this one equals, here this equals 0, that you will get Va plus Vb plus Vc, that one is Va plus Vb plus Vc, 20 plus 30, 50, 50 into that is 170 Here this is equation number 1. Then to get the value of the VA and VB and VC, then summation of MB equals 0. Summation of MB equals 0. Here we will consider the LHS of MB. LHS of MB. LHS of MB means we have to close this portion. Then by taking the moments of all the forces in the LHS of B, then we will get VA equals, that is, it will give us VA into, this one is clockwise moment, VA, that equals 1 over VA into 4. Here I will write directly the equation inside the bracket. This one is clockwise. Now equate the clockwise moment and anti-clockwise moment. Here this one is 20 into 1 plus 4, that is 5, that is anti-clockwise. Here by equating clockwise moment and anti-clockwise moment, here the moment, these two moments get 0, then VA into 4 already we have taken. This one is 30 into 2, that one is anti-clockwise moment. Here we are equating the clockwise and anti-clockwise moment, and this one is clockwise moment, that is minus 20. Then VA equals, we will get, that is 35 kilonewton, that is in upward direction. Then this one is positive. Then similarly summation of MB equals 0 for, here now we will consider the RHS of RHS portion, that is right hand side portion. Only consider these forces. Then here VC is the unknown, VB into 0, that is 0, that becomes moment is 0. VC equals, that is VC into 6, that one is anti-clockwise moment. By equating anti-clockwise moment with clockwise moment, here this one is clockwise moment at the support, that one is clockwise moment at the support. Then due to UDL, that is also clockwise, 20 into 6 into 3. Then at support there is a moment in anti-clockwise direction. Here that one is minus 20. Then by equating this, that is VC equals, here we will get 71.11 kilonewton. This is also upward, that is positive. Then by equation 1, VB equals, by equation 1, VB equals, that is 63.39 kilonewton. 63.39 kilonewton, that is also upward. Then to draw the shear force diagram for this one, here we will consider this one as the reference line for drawing the shear force diagram. Here this one is the ordinate. Here extend these lines below the support. Here start from the left. Here in the left portion there is a downward force as per the sign convention of the shear forces. Left upward is positive, come from the left portion. Here in the left the net force is downward, that is 20 kilonewton. Here from D to A it is remains constant. This one is the shear force ordinate. From A to D this one is negative. Here there is a support reaction VA just now we have calculated, that is this one is minus 20 kilonewton. That one is downward. Left upward is positive, left downward is negative. Here in this portion there are two forces, one is 20 and one is VA. Minus 20 plus 35, that one is 15 kilonewton. 15 kilonewton, that one is here because of this support reaction, that is minus 20 plus 35, that one is 15 kilonewton. Here this is the ordinate. This shear force remains constant up to 30 kilonewton force. Here again the shear force decreases because of this point load, that is minus 15 minus 30, that one is minus 15 kilonewton. Then Here from 30 kilonewton to B, the shear force remains constant, no other loads, hence the direction of the shear force is like this. This one is negative, this one is positive. Here the shear force remains constant from this point to this point. Here again there is a support reaction, that one is minus 15 plus 5 minus 15 phoebe. Phoebe is how much? That is 63.39. that is here the shear force is minus 15 plus 63.39. that one is 48.39 kilonewton. Here the shear force becomes 43.39. Then here in between B and C, the shear force varies gradually because of the UDL, that is here that becomes, here this one is the shear force changes from 48.39, that is 48.39 minus 20 into 6, that one is 120. Then that one becomes 86 point, that one is 71.61 kilonewton. Then this ordinate is 71.31 kilonewton. Here this is negative, this one is positive. Here the variation is like this. Here there is because of the support reaction, that is 71.11 at C. Then this becomes 0. If you want to draw the elastic curve, this one is the shear force diagram for this one. Here by observing this bending moment diagram, now we can draw the elastic curve for this one. Here in this portion these two moments are hugging. The bending moment is, it varies like this. Here here this is the bending moment, that is elastic curve. Elastic curve. Here this one is one of the point of contraflexure. This one is, here there is a point of contraflexure. Here again there is a point of contraflexure. Here in this portion the bending moment is sagging. In this portion the bending moment is hugging. Here at the support the bending moment is hugging, and here the bending moment is sagging. Here in this portion the total bending moment is hugging, hence the deflected shape is like this. Here this one is elastic curve. Elastic curve. This completes the diagram, that is bending moment diagram, this one shear force diagram, and elastic curve. We will continue in the next video.